Yeah, hello together to our statistics lecture. And before we start with our statistics lecture, I would show you, I think I've already done it, that I organized 2 talks in December. This week on Thursday from the Bundesbank is Julia von Borstel coming, and she is talking about monetary policy. And this will be, of course, a very interesting title, because we all want to know where the interest rates are going. So maybe I can see also somebody of you there. And then on next Tuesday, Dr. Lukas Nieu is referring about the hints for our government of our Council of Economic Advisors, and I think this will be also very interesting. And maybe I had the idea that we can have something like a happening after this talk. I don't know what's in English, Glühwein. Maybe we can then around 12 o'clock meet in front of the main building of our university. So maybe you can join. This would be nice. Then we want to go to our lecture. And as you have seen, I uploaded you the last topics, of course. Then the multiple linear regression. And I uploaded also some exercises. And yes, my idea is, please give me a feedback that you will not be in lecture on Monday, and therefore I would recommend that, as last time, you also start with the exercise by your own, and if you want, you can hand in me your exercises and I will have a look about it, and then we talk about the last exercises next week. Am I right about this? That I won't see you next Monday? Okay, then please have a look in the exercises, and I will just show you here. I uploaded this. So this will be some simple examples about doing by your own linear regression. Here you have already more or less the results of the linear regression, and then you should interpret these results. Another linear regression, and then I think 2 or 3 then a last exercise about multiple linear regression. Okay, so then let's go further on with our linear regression, and there we were by doing linear regression with a specific example, and this was, I think, where we are here. So, this hadn't saved last time, but you have it on the video. So let's go then to our Excel file and let's insert all this 70, 162, 940. So let's do it like this. All the sums. This is sum of y hat. Yep. And where we are here. And we had also calculated our dependence. Y equals ax plus b, and b we had 1.98 and a we had 3.92. And then of course we can answer the question. This is again something like a forecast that we can say, okay, what is the proposed sales volume for 30 visits? Oh, yes, I need, since I'm again alone here, I have to think about this. So what do I have then to do if I want to propose the sales volume of 30 visits when I have done my linear regression? So I have to wait. Now I see the chat again. And this is a 940, and then let's move this also. So what do I have then to do? Well, this is then my dependence, so I just insert that. This would be 3.92 plus 1.98 times 30, and this will be then roughly, stay here, y hat of 30 equals a plus b times 30 is roughly 63 or 64, 63. Well, maybe we can also put here a slide diagram. And so this is our data in a diagram, and we have here y and x. And here is also another possibility to calculate the linear regression via Excel. Here I showed you this is done by calculating the slope and the vertical point on the point on the vertical axis, or what we also can do is just do a right click here, and then you can here this you don't see, so at first I have to move it here and then right click, and then you have here the option to calculate the trend, and this you also don't see, then move it here. Then here we have linear trend, and we want to know the number, so please give me the formulas, and then we are done. So here you have, of course, then the same numbers. Let's take this also and put it in here. So for our linear regression. Okay. Then highly connected with the linear regression and these regression coefficients, which we can interpret as the dependence between the independent variable x and the dependent variable y. This we just have done here is that if we increase our visits by one visit, then the linear regression means that we will increase our sales volume by 1.98 or roughly 2 euros. Nothing else. This is so-called then the marginal distribution of our independent variable x visits to and the impact on the sales volume. And of course, this point A, vertical axis, just means if we look at this here, this would be down here, the roughly 4. This would mean we make a sales volume of 4 euros if we have no persons who can visit our customers. Well, but be careful, we will see this in our exercises with the interpretation of A. Mainly when we are doing these quantitative analysis, mainly we look then on this parameter B. So this is then quite often used, as we done it in our example, for forecasting or to obtain an idea what will change in my enterprise when I'm changing some variables. And now we want to come to the highly connected topic with linear regression. And this is, of course, the so-called correlation analysis. I think you have already heard about correlations. And that this is connected is more or less obvious. Then correlation just means also, is there any dependence between two variables? And then we would know, and actually we can also say that when we have here y and x, and you have your data point, then we always can, of course, oh, this you don't see, sorry. Oops. Then, of course, we always can calculate this regression line here. But then we want to know, well, how meaningful is this line of regression? So to speak, how near are our data points lying to our regression line? And for this, we then have the so-called correlation analysis, and this means that we want to calculate a measure which can say us how dependent we are, and for this we have the analyzation tool of Person, and this is the correlation coefficient, and this correlation coefficient can lie by definition between -1 and 1. And how do we calculate this coefficient of correlation? Well, of course, for this calculation, we need some measure of the dependence, and this measure of dependence is, so to speak, something for 2 dimensions which we already have calculated. Remember the concept of variance. Compare to variance, and this variance was, of course, just the sum of squared distances to our expected value. And if we have now 2 dimensions with x and y, then we use this concept of variance and call it now covariance, and we just insert for one x the other variable y, and still we are calculating this in the same way, that we multiply here now the distances between our data point and the average of our variable x, and the data point and our variable y with respect also to the average. Here you can also compare this with sigma, and then we can call it xx, so to speak, hat squared, and this was 1 over n minus 1 sum xi 1 to n minus x bar squared, or of course squared we can also write as 2 times these brackets. And with this number, then we can, more or less say that we have the correspondence between our 2 variables x and y via the correspondence. And of course, we can also say that this number can be also negative. Why is it possible that this number is negative and the variance not? Well, if we take the variance, then we can write this also as xi minus x bar squared, but these 2 numbers here can be, of course, greater or less than 0, and the sign, if this is positive or negative overall, can then of course also interpret it that if this number is negative, then we will have the tendency of the dependence between these 2 variables, that if x increases, that then y is decreasing. But of course, with this concept of covariance, we cannot really quantitatively interpret this number, because this can high, this can be low, and you see here, if we just would change the units of our variables, in which units we are measuring our variables, then this number goes up or down. We can calculate distances in centimeters, or we can calculate distances in kilometers. Let's say here the distance from my mouse to my pen measured in centimeters, then the covariance would be a really large number. And if I calculate this in kilometers, then it would be a really low number, 0.000, something like this. And oh, again, I have to shift all my slides, I see, that you can really see everything. But you have the slides at home. And therefore, we need a normalized version in order to interpret such a measure quantitatively. And for this normalization, we then divide more or less our coefficient of our covariance, which we have more or less here, by the product of the standard deviations of our single variables. And then this is covariance divided by the standard deviations. And with this, of course, then we normalize this. Take my example with centimeters and kilometers, because then, of course, we would calculate here, we would divide here both units through each other. This will cancel, and then we have here a dimensionless variable. And we can also show that this dimensionless variable is directly connected with the parameter of the linear regression. This was the parameter of the linear regression. Y is a plus bx. And this is also not very surprising. Remember, this was the slope of our linear regression, and if this slope is negative, then we have negative dependence. Then, of course, also our correlation coefficient R should be negative, and if we have a positive slope, then of course this correlation coefficient should also be positive. Well, and then we can interpret descriptively this number, and if this number would be more or less almost zero, then we will have more or less no dependence between our two variables. And if this goes up to 1, or let's say plus minus 1, so we can here write always plus minus, that we move then to a dependence which we interpret as, yeah, quite narrow dependence. Let's look at some examples. So what would you expect more or less for an R in these cases? Would it be in the neighborhood of 0? Would it be in the neighborhood of -1? Or would it be in the neighborhood of +1? What do you think? The first one. Or let's start with first, second, third, and fourth. Maybe let's start with this third. When all data points are lying on a straight line. What kind of correlation you expect then? A strong or a low correlation? What do you think? A strong correlation, yes, great. And then let's look here. Where would be our correlation coefficient then? Where will we find it? -1, 1, or 1. In this case here, and here we have supposed to be x and y. This should also be here. Oops. Y, x, y, x, y, x, and y, x. Well, if you have a look, well, this is always ending. No. So then, of course, we will be in this case, and we have, of course, a positive correlation, so this should be then 1. What do you think here? In this case, when our data points are totally symmetrically distributed. So in this case, more or less, our regression line would look like this. All data points are lying on one line. And then, of course, you can also think of by eye, what would be the best line which I can fit in this diagram. So in the neighborhood of +1, 0, or -1. So this would be strong positive correlation, strong negative correlation, and almost no correlation. Well, if we look at a data set where we have more or less random distribution, so totally symmetric, then we cannot distinguish between such a regression line, such a regression line, or such a regression line. what will be the best? I don't know. And therefore, of course, here we will have no correlation, and here we will have then R equals 0. What do you think in case 1? In the neighborhood of +1, 0, or in the neighborhood of -1? +1, great. Because here more or less we can fit something like this as a regression line, and then we can say, yeah, they are really, all data points are quite close to our regression line. So in the neighborhood of 1 plus 1. And what do you think in 2? Here maybe we can say relative to case 1. At first we have to determine the sign of our correlation coefficient, and then we can say, well, if this, I will show it to you in a minute, what is the number for this, then this maybe this is 0.9. Would it be then higher or lower than 0.9? But at first, if you have a look at the data points, will we have a positive correlation or a negative correlation? Also here, positive or negative? What do you think? You can really do it by eye, that you look at these data points, and if you would draw a line by eye through these data points, would this line have a negative or a positive slope? What do you think? Well, I would think, since we have here these points here and here many points down there, that more or less this will be something like this. So we will be here in this case. But of course, the distances of our data points are quite far away of this regression line. And then we have a negative correlation, but much lower than in case 1. And yeah, then we can think of this here maybe in the neighborhood of 0.4 or something like this. But let's have a look directly in our data, and I brought it to you here. This is the first example, the same example as we have in our example. We already talked about it. And if we again take this trend line, then you see here that you also have the option to show the coefficient of determination, and this is, no, you don't see it here. Here it is. This is just r squared. We will talk in a minute about r squared. So then we need the square root of 9.6 Oop, oop. So this will be then 0.97. In the next case, let's go here and also so square root of 0.22, and here of course we have 0 and 1. Let's calculate these two numbers. I think this was there, 0.47 and 0.98. So this is then right in the neighborhood of 1, and this was roughly 0.47. Okay, here we have already seen that quite often we are not talking about the coefficient of correlation, but about the coefficient of determination, which is thus the squared coefficient of correlation. And we will see that we can, the number which we have then here, our 0.98 or 0.47, that this is very intuitively interpretable. But we have to keep in mind that we then the dependence on plus and minus is vanishing. But of course, if we have in behind how our data looks like, then of course we also know that we have a positive or negative dependence. And what we can show is that this number r squared, more or less explains how good our regression, and this number explains us how much we can explain with our fit with the linear regression line compared to the total variance. And then of course 1 minus r means then what we cannot explain with our regression line. And in the two-dimensional case, this looks as follows. If we take the example here, because then the distances are a bit higher. Therefore, I chose this example here. Then we can say this would be our regression line. And then we can calculate the average of all data points. This is y bar. And our total variance. This is then the concept that we calculate all distances with respect to y bar. And then you can think that we now just switch our line where we calculate with respect the distances, that we switch this line to the regression line. And this means on average the distances of our data point with respect to the regression line are lower than the distances with respect to our mean. And therefore, we are then in this, roughly spoken, in a in a better situation that our distances have decreased. And this is meant by we are explaining the dependence via this linear regression line, and then we can show that this coefficient of determination, which is just the squared correlation coefficient, is the sum of our theoretical data points minus average squared divided by the sum of all distances with respect to oh, this is wrong. Sorry, this has to be x bar and not y hat. And the total distances of our data points with respect to the mean. And with this, of course, we can go again into our example and let's then calculate these numbers. This here. And what do we need? We need now y hat. And y hat, this you don't see. Now is then, of course, equals a plus b times our number of visits, 9. So this is the theoretical value corresponding to our regression line, and y equals 24 is our data point. And now we are calculating all our theoretical values. Y hat. So what we need then also is the distance of y hat minus y bar and y minus y bar. So y hat minus y bar, and this we want then to have squared. So this will be then y hat 21 minus 24 brackets and squared. And we want to have the two data points, so just y minus y bar, and this would be then 24 minus, oops, where do we have y bar? Sorry, here I also need y bar. This is not this one. So first I need to calculate y bar, and here we have the sum of y, so dividing by the number of our data points, and here we have 1, 2, 3, 4, 5, 6. So y bar would be 162 over 6. This is y bar, and then equals again y hat minus y bar squared and we have to fix these two numbers with the dollar signs, and now the same, y minus y bar, and also squared. I think here I have too much dollar signs because this is just up. There we are. Should be y hat and not be fixed. So, and then this we have to do for all our data points. And as we see here, we need the sums. So here we have already the sum. So sum and sum. And then we obtain our squared equals the sum of the theoretical distances to average divided by total distances. And then we have our 0.84, and R would be then square root of this. So then let's take this number and this number. Can I click in here? So then let's take this only with oops, and hopefully this works. No, now it works. And then we have, of course, 482.72 over 572 is roughly 0.84, and this would be then 0.92, I think. Yep, 0.92. Well, now we have a measure where we can interpret R square as the strength of the dependence between x and y, and we can then say that we have a measure with where we can interpret this as the proportion. So here in this case, then we can say with our linear model, and this was y equals 3.92 plus 1.98 times x, we can explain 84% of the dependence between x and y. And then, of course, we can say that if we have an r squared of 0, this would mean that also our slope of the regression line has to be 0, and therefore we have no influence between our two variables. Because if we have 0 times x, then nothing happens to y, and if we have r squared equals to 1, then of course all our data points are lying on our regression line. Oh, no, what's happened now? Here we are, sorry. Let's move this now. This has to be here. And so let's do this. Well, that's it for the two-dimensional case. But of course, as always, we have in the real situations not only dependencies between two variables, but we have many dependencies between variables and other variables. And in economics, well, we can say we started with the dependence of sales volume on visits, but we can say, of course, it depends maybe on the marketing budget. It depends on how many stores we have, how many branches we have, and so on and so on and so on. So we can think, of course, of many, many variables. And this, of course, we can also put in a linear model. With this here, we started. This was our starting point. But now we have x1, x2, x3, and so on. And then we just put these numbers, these dependencies also in our linear model. And then we become this multi-dimensional sum. And of course, then for all single variables, we will have to collect data. And then we have to put these data, we have to collect it, our observations, into our model. And again, as we had it in the simple linear regression, our data points in general will not always fit for 100% our assumed model. And therefore, we will then, for every data point, a slight discrepancy between our model and the corresponding y, corresponding dependent data point. And this, of course, then we can put in a linear system, and I think this you have done in mathematics, that then we are using vectors and matrices. So this is, it looks quite complicated, but this is just what we have here, because this line here we of course have to write down for every data point we have collected. So if we have a sample size that we asked 1,000 people downtown Wilhelmshaven if they want to eat chocolate, then we have 1,000 data points. And this we can write in a compact way in a matrix and vector combination. And you see, then we have, of course, a dependent vector y. This is now our sampled data for all independent variables x. This will be our regression parameters, and these are our error vector of regression parameter and vector of errors. And this is vector of dependent variable. Well, and again, of course, we want then to minimize the sum of the squared errors. And how can we do this? Well, from this we can of course then just write epsilon vector is y vector minus x b vector. And this we just square, and this we want to minimize. Well, and as we have done it, I think I put it also for you here in the simple case. Where did we have it? Here. This was in the two-dimensional case our function which we have to minimize, and now of course we have not only one error, but we have this vector of error. So this is also then a multi-dimensional function, but we have to do nothing else than to calculate the derivatives with respect to our regression parameters. But now we have not only two, but we have k plus 1 derivatives to calculate. And I don't know if you have done this in school, but this has to be done via vector analysis. So you have to calculate multidimensional derivatives. So this is then the derivative with respect to a vector. But there something very similar happens as in the simple linear regression case. Let's look at this here. Minus 2 times the transponed matrix times y. This looks quite similar as in this case here. Here we have also our minus 2 and a plus bx, and in this case here also xt times x times b, and remember within this vector b now we have our simple parameters a plus b. And these are our first order conditions. These we have to solve. Then we have this condition here, and this condition has to be solved. For beta, well, if you have only the simple linear regression, then we would just divide, if this is a number, by this number to obtain beta. And if we are in the vector calculation, then of course we have here just to calculate the inverse of this matrix. So this is the inverse of matrix xt x. Oops, this I have 2 times here. And everything is done more or less in the same way as we have done it in the simple linear regression. Of course, again, when we have solved for all our betas, the coefficient of determination is, of course, still defined as the relation between the theoretical values minus average divided by the distance calculated by the data points minus average. So here really nothing changed. And now we want to go to some example, and there we will add some more variables. We start with our visits example, and now we want to introduce a variable with we can calculate the marketing budget and if a branch or a store is located in our region. Well, for this, of course, we have numbers. So we collect how many visits did we have. And also we can look what was the marketing budget for the last quarter or for the last year, maybe. But how can we quantify the impact of the situation that we have a branch in our region? Well, in order to quantize this, we then introduce a so-called dummy variable. And for this dummy variable, we say if this dummy variable is 1, then we have a branch in the region, and this dummy variable is 0 if we have no branch in our region. Well, then let's take this example here, and this is then a homework for you, because this takes some time, that you should calculate the regression parameters beta I, and for this actually you just need these formula here. So what you need at first is what is xt Then you have to calculate the inverse, calculate the inverse times xt, and in the end multiply this with your data points for y. Well, of course, this you have in every software package that you just fill in your data in your software package and then press enter. And if you do this, then we obtain these numbers here, that we have a beta 0 of 10, a beta 2 of 1.48, a beta 2 of 0.7, and a beta 3 of roughly 9. And the coefficient of determination will be then 0.93. Now my saving takes some time. And yeah, what is again our interpretation of these numbers? Well, this means our model explains 93% of the dependence. Beta 0 is hard to interpret, because what would beta 0 mean? This would mean that we have, if we have no visits, no marketing, and no branches, that then we would have sales of a volume of roughly 10. There, of course, as that you have to be careful to interpret this like this. But in this case here, you can think that if we increase visits by 1, then sales increases by 1.4. And here we can interpret if marketing budget is increased by €1, then we have sales increased by 70 cents. And here, if we have a branch in the region, we will have additional sales of €10. So again, of course, these regression parameters are interpreted in the same way as in the simple case. But until now, we only have done descriptive statistics, and this you really have to keep in mind. So we just collect our data, and then we say from our data we find some correlation. But we definitely have no causality between our two variables, because this correlation we can also calculate from what is the weather like outside, and how many babies will be born in the next week. And of course, the weather, we don't know if this is really the right variable to explain the birth in our hospitals in the next 2 weeks. So please do not mix correlations with causality. And also, quite often, we ask 1,000 people what are their preferences for some new goods we want to produce. But of course, we do not want only to sell our product to these 1,000 people we ask. Then we want to sell our product to all people in the region. But we have only the information of these 1,000 people we ask. Maybe you are doing something like this in your bachelor's thesis, or you will do this, and then we have to have an idea how good is our data that we can interpret the answers of these 1,000 people, that maybe from these 1,000 people 80% said that they want to buy this new product. Then I want to have an idea how good are these answers in order to conclude that also many people in our whole region will buy this new good if I start to sell it. So what kind of conclusions can be drawn from our survey data, from our sample, to the whole population, for the whole region? Or if we have find in our data set a high correlation, can I then also draw the conclusion that the correlation for the whole region, for the whole population, is also high? This we haven't answered right now. And for this, that we can quantify this, how good is our data set, in order to take the numbers we calculated there for the whole population, we have also to make, of course, some assumptions, especially about the error terms we had in our model. Remember, where did we have our errors? This was here. And then if we know how these error terms behave, then from statistical analysis we can make conclusions and say with some probability we can draw conclusions from our data set to the whole populations. And how this is done and which assumptions we need, about this we want to talk in the next minutes. So with these assumptions, we then can make a probability statement. Let's say with 90%, we can say we can directly draw the conclusion that we have, if we found in our data set a high correlation, that we also find a high correlation in the whole population. And this is what we call hypothesis testing. So what we are doing then is that we make, for example, the hypothesis testing, the hypothesis test. Let's say we found in our sample an R² coefficient of determination of 0.8. Can we say with 90% probability that we find also in the whole population a coefficient of determination of 80? And how is this hypothesis testing made on specific assumptions? And first of all, we think that the expected value of all our single error terms is 0. And this means that we have here in our error terms no bias. And this seems quite reasonable because otherwise we would just subtract this bias and then we come to an error term which is distributed around the origin. What is also really important, and quite often the people forget about this, is that all our variables have to be independent. And of course, let's say our example with visits and marketing budgets. There can, of course, in practice be a dependence between these two variables, visits and marketing budgets. But in our model, we assume that all these variables are independent and also that the error terms are independent. And then, and this is maybe the strongest assumption we make, is that our error terms are always all distributed in the same way. So they all have the same variance. In practice, this will be very seldom the case. And this is called homoscedasticity. And in general, we have to test also on this assumption. But in our case, we will assume that every variable has the same variance. And I talked already about this, is these independence. And these independence means, remember that our covariance between our error terms is 0. Well, this just means that these two errors has nothing to do with each other. And this is called that there is no autocorrelation. And then that we really come to some quantitative number, we not only say that we are distributed about the origin, and we are distributed about that they all have the same variance. We also assume that all error terms are normally distributed. Well, this looks like a really hard assumption because in general, of course, we have to admit what shall we know about the distribution of our errors. What could be the argument that this is a practicable assumption? Because we really know that in general we don't know what the distribution of our errors is. And I think this you have already heard in other statistic courses. Why do we quite often make this assumption of the normal distribution of errors? Why do we very often make the assumption of normally distributed errors. Do you have an idea? Well, why do we call this distribution normal distribution? Remember, this looks like this here. And f of x is then 1 over square root of 2 pi x minus mu over sigma squared. This was the density function of the normal distribution. Well, this was the central limit theorem. And this you always have to keep in mind. And this is the reason why we then start, if we collect our data, that we not only talk to 100 people, but roughly to 1,000 people. Because then, if the number of our data set increases, we know that although we don't know how our variables are distributed, that we come closer and closer and closer to the normal distribution. So this is the most important result, I think, in statistics, this central limit theorem. Well, and if we have made these assumptions, then we can also think of what we have done in the one-dimensional case already is then, what would be a good estimator for our distributions? And good estimators are, of course, again, just the arithmetic mean, but what would be a good estimator for the variance? And there at first, we could think that we have again these unbiased variance which we calculated in the one-dimensional case, where we had to divide our sum by n minus 1. But in general, we can say that this estimator would still be biased if we look not only at 1x, but at x1, x2, x3, and so on, so that we have more variables. And therefore, we can then show that we have to change this factor into this factor, and there we subtract not only 1, but we subtract by k plus 1, and this just means that we have to subtract from our sample size the number of regression parameters. And what does this mean? Well, intuitively, we subtract here the numbers of degrees of freedom. So this means intuitively subtracting the number of degrees of freedom of our model, because the number of our parameters, this determines then within our data set in our model our dependence, and this we cannot change anymore. And therefore we call this degree of freedom. And then this we won't show here in this lecture. We can show then that our estimators have all then variances which are, not surprisingly, dependent on our first order conditions of our linear regression. And since every single error has the same variance, which we estimate via sigma hat, we then multiply this general variance with our regression matrix, and then we obtain the errors of all our parameters. And then, of course, we have to take the square root, and the square root of these numbers here, these variances, is then called the standard error. And what we can then show, if we assume 1 to 5, these assumptions here, that then also our estimated parameters are normally distributed around the true parameter with from our regression model estimated standard deviations, our variances. And with these calculations, then remember we have our model here. Y is beta 0 plus beta 1 x1 beta 2 x2 plus beta k xk. Think we have estimated now all our parameters, and beta hat I, think you have calculated beta I hat and r squared. With these numbers, then some really smart guys showed that with these f value here, just calculated from these r squared here, has a specific distribution, and this is called the Fisher distribution. And what is the Fisher distribution is about, this we will talk on Wednesday. And that our single regression parameters also have a special distribution if we calculate these so-called t-values, and this is called the student distribution. And with these two testing parameters, then we can make some statements about how good are our parameters and how good is our estimated correlation in order to conclude from this a statement for the whole population. And how this is done, we will talk then in 2 days. And this is the so-called F-test and T-test. Okay, then we are done for today.